Okay, today we will study more about the convolutional operation. Here shows a input signal xt. Okay, this one is input xt. Okay, so input xt is sampled by impulse function, approximate impulse function. Approximate impulse function is this one, delta and t. Delta means the time step, so it can be plotted with a time function. Okay, it looks like this kind of impulse. This impulse function exists only 0 and time step delta. In between 0 and delta, it has a value 1 of delta. The area is 1. So this is the approximate delta function definitions. It has only non-zero value at the in between 0 and the delta, and except that all the way 0. So this is the impulse, approximate impulse. By use of this impulse, we can sample the xt. For example, let's consider this impulse. Okay. In this impulse is a all the way 0 and non-zero in between 0 and the delta. So time step is delta. So this function can be expressed like this way. x0 is this value. x0 value times delta t times delta. So this function is function of time. Okay, function of time. So this is time axis, all the way 0 and impulse and goes to the 0. And the next column here, let's consider this function, this impulse. Okay, this impulse, the value will be x delta times impulse function. And delta should be multiplied. You know that this is always 1. This is 1 and this is 1 because of the area as unit. So this is this time functions. And let's consider another one more. Then let's see this impulse. Okay, this function, time function, can be expressed as k delta times impulse function times delta. So this function corresponding to this one. So summing of all the pulse trains, k changing from minus infinity to infinity, then it will look like this staircase approximate signals. That's the x hat t. So x hat t is an approximation of xt. But x hat t decompose many scaled impulse functions. Scaled impulse function summation is x hat t. By taking limit delta goes to 0, x hat t becomes xt. And you can see here that the summation becomes the integration, and delta t change to d tau, and changing from minus infinity to infinity. And here you can see k times the delta becomes the tau. Okay, like this one, it becomes the tau. So x tau times delta t minus tau times d tau. By definition of the delta function integration, it will be given like that, because delta t minus tau as a non-zero value, only t equals to tau. Only at this time it is non-zero, all the other time it's 0. That's why after the integration it becomes this one. So this means this one, and this also means this one. Oh, okay. So at this moment you can think about that the xt can be decomposed into impulse train, summation of impulse train. Okay, you can approximate this one, the summation of impulse train. And here, if we apply the delta function at the input, then the output is impulse response, like that. So that's this one. What if we we assume that this system is linear and time invariant. If this system is linear and time invariant, then we can scale the impulse function and time shifting. Then the same scaling and time shifting occurred at the output. So let's try this one. At a specific time tau, x tau, is this one. You can think about this one. This is x tau. Okay, this is x tau. Okay, and this is scale factor for the delta function. Delta function is time shifted. T minus delta tau. So we scaled and shifted, but the system is linear and time invariant. Then if we apply this input to the system, the output will be x tau. This is scaling factor times h t minus tau. Okay. If we apply the x tau scale and the delta function is shifted by tau, then output will be scaled and shifted. It's obviously. So because this one is homogeneous, it means the multiplication conserved. Okay, so the scaling factor just the product, and this is a time function. But the shifted one, because of time invariance, it gives just shifting the output response. And also the linear guarantee the additivity. It means if you're taking integration, the integration is supported like that. So if you're taking minus infinity to infinity d tau, then this also satisfies this one. And this one, as we defined, xt. If we applied input xt to the system, then output will be given as yt. Okay, we derived convolutional theory. Input xt can be think about impulse function, scaled and shifted impulse function. Then system is linear and time invariant. Then scaled and shifted should comes out, and linearity guaranteed the additivity property. So by taking integration minus infinity to infinity, that becomes the input signals. Okay, this one. Then output also taking integration the same range. So that is the convolutional theory. So from here we talk about the output is minus infinity to infinity, minus infinity to infinity x tau times ht minus tau and d tau. This is the output. It's the same things. We have in case of approximate versions, k delta, we can approximate that one. Oh, delta should be ghosted. It's a typo. So this is the convolution theory, and similarly we can think about the inversely change of variable. You can prove that this one is the same thing. This means that the commutation property, it means that if xt is applied to a system ht, it's the impulse response ht, then this is the output for the x convolution h. X convolution h are this one. But the second thing, you can compare this one. It seems like this one. ht applied to a system of impulse response is xt. Then output will be h convolution x xt. It's the same thing. So we can interchange the impulse response and the signal, input signal. It doesn't change. So that is this property. We call this as commutative. Commutative property are valid in the convolution operation. Okay, so that is this one xt, and system function ht are interchangeable. So at this moment we talk about the xt signal is applied to system ht, but interchangeable means that the system function ht is applied to the xt signal. So it's the same result. And the next one is if a system is causal. Causal means that the impulse response always occurred. This is positive cases. It means that the ht, you know that ht is a non-zero if t is positive. Okay, so in the integration, so t minus tau should be positive to have non-zero ht value. If this condition, ht is non-zero, but the t minus tau is less than 0, ht is 0. Okay, keep this better. It means that the t minus tau is non-zero. Else, t minus tau is negative, then t minus tau is 0. So because of this one, we always integrate over these times. So tau always less than t to satisfy these conditions. This one means the causality. It means that the impulse is given, and here response should come after the event, cause and effect. Okay, to satisfy this one, the argument of h should be positive. To be positive argument, t minus tau should be positive. To satisfy that one, tau always less than t equals 0. So tau can be changed minus infinity to the only t is possible. Okay, t is the maximum value of tau. So this is causal system cases. In these systems, we can try to using the change of variable t minus tau replaced by tau prime, then tau, and we know that the tau changing from minus infinity to t. Then tau prime, let's replace minus infinity at here, that becomes the infinity, and up to t. T replace the tau, then tau prime goes to 0. So by change of variable, tau prime will change minus infinity to 0, and the d tau prime is minus d tau. Due to this minus, integration direction from 0 to the infinity, we can using that one, and h tau prime. So we take this one as a tau prime, and tau are t minus tau prime. Okay, this is also valid. So we talk about what is convolution theory, and think about any input signal can be decomposed into impulse train, scaled time-shifted impulse train. So system is a linear and time invariant. We know that the impulse response, then scaled and shifted impulse response will be scaled and shifted output response. So due to the additivity of linear property, we taking integration at the input signal, then we just the integration, the same thing at the output signal will give the total output, and this one gives the input signal. So input xt decompose into the scaled impulse train, and the output is a sum of impulse response with a scaled and shifted one. Okay, that's the convolution operation. We already talked about the two different examples from here. The rectangular first function is shifted to 0.5, and then it will give this kind of pattern. This one is the rectangular pulse shifted by 0.5, and impulse response is triangular like that. So impulse response is 1 minus t during these times, although the case is 0, so it has this kind of impulse response. So you can think about this one is a causal systems, and from here we can calculate the convolution. Okay, from here you can see x tau times xt minus tau is producted and integration will give the output. So you can calculate the area, or you need to calculate the area. To calculate the area, we can using the geometric method or the integration method. First, try the geometric method. Before that, I would like to see the function of this one. ht is given like that, but you need to keep in mind that this axis is tau. So I would like to plot this axis is tau. ht minus tau should be plotted firstly. So this function looks like this one. Because it's reversed and scaled, this is t. And this point is t minus 1. Okay? So think about this one. If tau are equals to t, tau becomes the t, then the argument of impulse function is 0. So that's this point. So, and what about this point? If tau are equals to t minus 1, replace here, then it becomes 1. So that's this point. So this point corresponding to this one, this point to the 0. So because this is reversed and shifted, this is the function. Let's consider first if t is less than 0. In that case, the ht minus tau shapes looks like this one. This is t point. If t is less than 0, the product between x tau and ht minus tau will goes to the 0. Then output is always 0. Now the second time, t is between 0 and 1. In this, if t existed between 0 and 1, its shape looks like this one. So green one shows that. In that case, the product area becomes this trapezoidal function, this trapezoidal shape. Okay, we have to taking integration over here to figure out this area. The third one, if t is greater than 1 and in fact less than 2, so t is greater than 1 and less than 2, then it looks like this one. So the calculation area becomes a triangular of this one. And lastly, if t is larger than 2, in that case it looks like this kind of functions. So by producting of these two shapes, yt goes to 0. Okay, think about this period. At this period we have to calculate this trapezoidal area, this area. So this height is 1, and this distance, we know that if this is t, then this point is t minus 1. Then this distance should be equals to this distance. So this value will give t minus 1 and absolute value. But at this moment, we know that the t is less than 1, so t minus 1 is negative, so it should be this value. The positive number is this one, so this is this number, and this was 1. So yt equals to area of that. To calculate the area, the trapezoidal area is a average of these two values. So that's the 1 minus t plus 1. So this one is this one, and 1 minus t is this value, and times the length of this one, t. So it will give, if you multiply this 2 and 1, and t minus 1.5 t square. Okay, this is it. Then what about this one? In this period, yt are given this triangular area. So if this is t and this is 1, and this point is t minus 1. Okay, this is t minus 1. So at this moment, this distance This distance is 1 minus t minus 1. Okay, this height is the same, so yt can be given as the area of triangular area is 1.5 times, so width times height. Width is 2 minus t, height is also 2 minus t. So this distance from here to here, distance 1 minus t minus 1 gives this distance. So it will give t square and divide by 2, 1.5 t square. And minus 4t becomes minus 2t. And 4 divided by 2, that will give it 2. So this is the output yt in this period, this result. So we got all these things. Try to compare the iteration method. In the iteration method, it will show the same result. In these conditions, it goes to the 0. That's these two parts. And if t exists between 0 and 1, then it will give t minus 1.5 t square. That's this one. And if t exists in between 1 and 2, and it will give this result. Okay, I hope that you may understand what is the convolution operation. To understand the convolution operation, you need to firstly understand the decomposing the input as a impulse sequence. Scaled, shifted impulse sequence is the input signals. So input signal can be decomposed in that impulse train. So and rely on the linear and time invariant property of the system. If we assume that the system is a linear and time invariant, then scaled and shifted and summation can be applied input. The same operation applied to the output. Scaled and impulse response is shifted and the sum. That will give the output. Basically, this one is related to superposition theory. So lots of many impulse trains are applied into this input that corresponding to input xt. Then we can figure out the summation of impulse response, scaled summation of the impulse response. That's the convolution. And the same convolution can be understood by these examples, how we're going to calculate that one. Keep in mind that one. And we also solve the same problem. Here is a rectangular pulse. Two different rectangular pulses are convoluted. Then you can figure out that becomes a triangular shapes of signals. And also try out the convolution of exponential functions. Okay.